Welcome back. Today we'll begin our study of formal deductive logic, which has important applications in mathematics, computer science, and philosophy. As interesting as these are, for our purposes we'll be studying sentential logic, also known as propositional logic, as an aid to critical thinking and argumentative proficiency. To do this, we'll need a method for formalizing both the content and the syntax of the sentences we use in English in order to achieve the clarity and precision we desire. Arguments are composed of declarative sentences, and sentences can be problematic in logic because sentences are often ambiguous. That is, they can have more than one meaning or refer to multiple states of affairs. Ambiguous sentences pose problems for logicians because they can be true in one sense and false in another. Because logic has to do with the truth and falsity of premises and conclusions in arguments, if it is not clear whether the component sentences are true or false, serious difficulties can arise. We can avoid these difficulties by limiting our study to sentences that are either true or false, which are declarative sentences. Questions like, "Is Jack at home?" Commands like, "Shut the door, Jack," and exclamations, "Wow, is Jack happy?" These are never true or false. We can only work with sentences that are definitely one or the other, true or false. And we'll make things even simpler. We won't bother with the usual grammatical distinctions between the parts of a sentence, such as subject, verb, and predicate. In fact, we'll ignore the internal structure of the sentence altogether and instead treat it in the simplest possible way by symbolizing the entire sentence with a letter of the alphabet, say the capital letter A. So for a sentence like "Ava loves football," we could simply use the letter A as a stand-in or substitute for it. Similarly, we can let other capital letters stand for other sentences, as in the following. Let the letter B stand for "Walter eats bread," and let the letter C stand for "Charles reads books." In sentential logic, the individual sentence letters, such as A, B, and C, are called atomic sentences because they're the basic building blocks out of which more complex structures are made. In some logic texts, by the way, atomic sentences are called simple statements. We can identify atomic statements in natural language, such as English, as well. An atomic sentence is one that cannot be broken into smaller parts that are themselves sentences. So the word atomic indicates that these are the smallest units of sentential logic that we need to consider. And here's a very important note. Sentential logic is bivalent, in the sense that each and every atomic sentence must be either true or false, but is never both true and false at the same time. And although the symbolizing letters can take on different meaning when used in a different context, they will always have the same meaning and truth value within the discussion at hand. Starting with atomic statements, we can create more complex sentences, known as compound sentences, by employing a kind of logical glue in the construction process. This logical glue is composed of unique sentential connectives, of which there are just 5. First, negation, expressed in English by the word not, or the phrase, "It is not the case that." For example, we could take the atomic sentence, "Ava loves football," and simply deny it by saying, "It's not the case that Ava loves football," or "Ava does not love football." We can also view the two opposing claims, that Ava loves football and that she does not love football, as contradictories, since they have opposite truth values. Second, conjunction, most often expressed in English by the word "and." For example, we could conjoin two sentences as follows. Walter eats bread and Charles reads books. Note that each sentence, when conjoined, is known as a conjunct. Third, disjunction, expressed in English by the word "or." For example, we could disjoin our two sentences as follows. Walter eats bread or Charles reads books. Note that each sentence, when disjoined, is known as a disjunct. Fourth, the conditional, expressed in English by the use of "if" and "then." We could place our two atomic sentences in a conditional relationship as follows. If Walter eats bread, then Charles reads books. By the way, the sentence that follows the "if," in this case Walter eats bread, is called the antecedent. The sentence that follows the "then," in this case Charles reads books, is called the consequent. Every conditional sentence will always have these two parts, the antecedent and the consequent. Last, the biconditional, expressed in English by the phrase if and only if. We could place our two atomic sentences in a biconditional relationship as follows. Walter eats bread if and only if Charles reads books. As with atomic statements, each of these 5 statement connectives can be symbolized, but unlike the capital letters used to symbolize atomic sentences, their meanings can never change. They are logical constants. Here are the symbols we'll use for these connectives. For negation, we'll use the squiggle, which we'll call the tilde. For conjunction, we'll use the ampersand, which looks like this. For disjunction, we'll use the wedge or the V, like this. For the conditional, we'll use a horseshoe, which looks like this. And for the biconditional, we'll use the triple bar, which will symbolize like this. This is a good point to review the terrain we've covered so far. Here's a video from Kevin Delaplante that will do just that. 2 things to note. First, some of the symbols that Professor Delaplante uses for the connectives differ from ours, but they have the same logical function. Second, he does not discuss the biconditional. Yet.
Propositional logic is sometimes called sentential logic or statement logic. An argument is a set of claims, and the term claim is synonymous with the terms proposition or statement or assertion. A claim or proposition is a bit of language that has the following defining feature. It's the sort of thing that can be true or false. So propositional logic deals with logical relationships between propositions. But more importantly, it deals with logical relationships between propositions taken as wholes. And by this we mean that in propositional logic, the fundamental unit of analysis is the whole proposition, the thing that can be true or false. We're not interested in the parts of speech that make up the proposition, like subject terms and predicate terms. In John is wearing a red coat, for example, John is the subject term and is wearing a red coat is the predicate. So the subject term John by itself is neither true nor false, and neither is the predicate phrase is wearing a red coat. So only when you put them together do you get a whole proposition that can be true or false. So in propositional logic, all we care about is the truth value of a given proposition, whether it's true or false. This is why in propositional logic we use single letters to symbolize a proposition. So we might symbolize this proposition with the single letter J, which will stand for the whole proposition. John is wearing a red coat. Once you've done this, then you can ask how the truth value of this proposition relates to the truth value of other propositions. Or you can ask how the truth value of a compound claim relates to the truth value of the individual component claims that make it up. Here's an example. John is wearing a red coat and he's stolen a Jeep. This is an example of a compound claim or compound proposition. It's composed of 2 claims. John is wearing a red coat and John has stolen a Jeep. Each of these component claims is a proposition that can be true or false. We can ask, is John wearing a red coat? If he is, it's true. If he's not, it's false. Similarly for whether John has stolen a Jeep. Now, from the standpoint of propositional logic, what's really interesting about this example is that the compound claim as a whole is also a proposition that can be true or false. In this case, it turns out that the compound claim as a whole is true just in case both of the component claims turn out to be true. Either one is false, and the compound claim as a whole will be false. So if it turns out that John has stolen a Jeep, but he's actually wearing a blue coat, then the compound claim circled in green is false. This is an illustration of the general point being made in point number 3 above here, that propositional logic is concerned with the way that the truth value of compound claims is a function of the truth value of the individual component claims. In propositional logic, you construct compound claims out of a small number of basic logical connectives. These are the basic types. You form conjunctions using and, you form disjunctions using or, you form conditionals using if-then, and you form contradictories using not. Once you know the rules for how the truth value of these compound claims is a function of the truth values of the component claims, then you can evaluate the truth value of more complex claims like this. If A or B is true, then C is true, and D is not true. Given the truth values of all of the component claims, you can work out the truth value of the compound claim.